Okay, so now we're going to start talking about gravitation and Kepler's laws. And so to get started, let's go over our formula sheet and just talk about some important formulas. First of all, this is our formula for the gravitational force on something. Here we have our formula for gravitational potential energy. And this one is also gravitational potential energy, but this is when you're close to Earth's surface, and this is when you're not close to Earth's surface. And R in both of these represents distance from the center of mass. Okay, when we use this equation, H represents the distance from the surface or from some relative position. R here has to mean the distance from center. Okay. And let's see some other equations. So this is going to be important when we talk about gravitation, because this is where Kepler's laws kind of connect. And this is that for objects that are orbiting some other body, their angular momentum is conserved. And this right here is the reason why things in space are spinning and orbiting each other, because angular momentum. And then a couple other things that are going to be relevant is this formula here for period, okay? In addition to kinetic energy, and this equation is going to come back again, okay? That work is equal to the integral of the force with respect to radius, which means that potential energy is equal to the negative integral of force with respect to radius, which means that force is equal to the negative derivative of potential energy. Okay? And if you apply this to this equation here, that's where this equation comes from. Okay? And these are really the most probably relevant formulas that we use for gravitation. Now there are other formulas that we use that are not on here. So for example, Kepler's third law, which T squared equals 4 pi squared over gm times r cubed. Okay, and that comes out of applying, and this one too is important here, centripetal force to Newton's law of gravitation, and this equation right here, out of that we end up getting this equation here. In addition, when you talk about escape velocity, that has to do with energy. It comes out of equating the kinetic energy of something to the amount of gravitational potential energy it has. Okay? And then orbital velocity for a circular orbit is going to come from equating the centripetal force to the gravitational force. Okay? And this will tell you the orbital speed of something. It can also lead to this equation here. Okay, but instead of memorizing these formulas, what's a better approach would be to understand where they come from and the concept used to set them up, because you get them just from putting other formulas together. And if you understand the concepts behind them, then it kind of takes away the need to memorize them, because you understand what's going on there. And if you want to go more into where these formulas come from, you should go back and watch some of the gravitation videos. Okay, so for this one, satellite of mass m is in stable circular orbit around Earth at a distance r1 from the center of the Earth, and it says the mass of Earth is m sub e. Then asks us to derive an expression using these terms and fundamental constants as appropriate. The first one would be the orbital speed of the satellite. Okay? So the way we would do this is we know that if it's in a circular orbit, okay, it's a stable circular orbit, so that we know that, first of all, for the satellite, if this is Earth and that's the satellite, the only force acting on it is that gravitational force from Earth, okay, which is equal to gm over r squared. The big M is m sub e, little m is the mass of the satellite. Okay, now this is equal to the net force, which generally we use ma, but since it's rotating, we're going to use centripetal force, mv squared over r. The m's will cancel out. Okay, one of these r's will cancel out, and then v will be equal to the square root of gm over r, all that stuff. Okay, that's part one, the orbital speed. Then it says, well, what's the total energy of the satellite? Assuming gravitational potential energy to be zero at infinite distance from the center of Earth. Okay, well, we know that the total energy is going to be equal to the kinetic energy plus the potential energy. Now, when it says gravitational potential energy to be zero at infinite distance from center of Earth, that's telling us that U is equal to negative gm over r. Where that comes from is when we integrate the force to get U, we're integrating from infinity to r, okay? And so that's basically how we find this value. That's where this equation comes from, and so it's basically telling you that this is the equation you should use, okay? So kinetic energy is 1/2 mv squared. U is negative gm over r. Now, the problem we have is it says that we're not allowed to use, I don't see v up here, so we can't use v. Okay, but we know that v is equal to the square root of gm over r, so we can go like this. 1/2 m times the square root of gm over r squared plus negative gm over r. Okay, when we square this, we get 1/2 gm over r plus negative gm over r. So when we combine these, this is like negative 1 plus 1/2, and so we get negative 1/2 gm over r as our total energy. From here, we haven't quite answered this correctly just because we haven't used these exact terms, so we can either say that r, make a key that r is equal to r1, and that big M is equal to m sub e. Or you can rewrite it as equals negative g me little m over r1, and then the 2r1 right there. Okay, so that'd be your answer for the second part. Alright, now move on to the third part of this question that says the rockets fire and lift the satellite. So here we have this orbiting satellite. Here was its initial path, r1. It's going to get boosted to r2 times that initial distance. So it's going to double its radius. And it's going to follow this path right here, travel some distance s. Okay? And then we have this equation for the force it experiences during that transition. So these boosters are going to fire, I think, maybe slowing it down, kind of pushing it out to this greater orbit, this greater radius for its orbit. And so we want to find work. Okay, well, work is going to be equal to, remembering from back up here, work is equal to the integral of force with respect to the radius. So work equal to integral with f, and we'll just say dx here because it's using x for distance. Okay, and then when we set our bounds, well, the distance it travels is this distance s, and the whole time the force of the rockets is parallel to that path. Okay, which means that they're doing work the whole time. Remember, because work is that parallel force times the distance. Okay, so we're going to integrate from the starting point 0 to this ending point s. So f is equal to, so integral from 0 to x of f naught times 1 minus x over s dx. Okay, so we can pull out f naught, and then to integrate this, this is just going to become Okay, so when we integrate, the 1 is just going to go to x, and the negative x over s, we're going to increase the exponent to 2. We have to divide them by 2, so it becomes x squared over 2s. Okay, and we're going to evaluate from 0 to s. Alright, so when we put 0 in for x, then this just becomes, we'll start with s. So when we put in s for x, we get f naught times s minus s squared over 2x, and then minus f naught times 0 minus 0 squared over 2s. So this term will go to 0. So we simplify this first term here, we get f naught times s. S squared over s just becomes s, so this is s over 2. All that simplifies just to be f naught s over 2. Okay, so that's equal to the work. And finally, we want to know, it says if s is equal to 3r, drive an expression for f naught in terms of m, r, m, and fundamental constant. So basically, the work is going to be equal to the negative change in potential energy, or the potential energy at R1 minus the potential energy at R2. Okay? The work equal to F naught S over 2. We're going to put in for S, we're going to put in 3R1. Okay? For R1, we're going to put in G, M, M, negative G, M, M over R1. For R2, we're going to put in negative G, M, M over 2R1. Okay? And unfortunately, I'm not going to be able to solve this for you. The reason I have to keep pausing is because I'm holding a 5-year-old baby right now. But I'm going to put down an answer for you to show you what F naught is equal to. So F naught, when you simplify all this, is equal to, this ends up being to G, M, M over 6R1 squared. Okay? And so this is our video on gravitation. Alright, let me know if you have any questions.